Hello everyone. What you just saw was the relatively modern task of taking a screenshot on my 6502 single board computer and then saving it to my 1972 Sony TC252W reel-to-reel tape deck using my simple universal modem and then reloading the screenshot from tape. I stopped halfway through the load, causing the artifact in the middle of the screen. If that sounds super weird to you, I suggest you take a look at my previous videos about my 6502 computer first. In this video, I will show and tell a bit about how saving data to ordinary tape became a thing in the 1970s, why that was a good idea, and why I decided to make this simple universal modem. After setting the scene with that, I will give a short presentation of this simple modem and show how to hook it up. I'll then demonstrate what saving to a modern PC looks like, and talk a bit about how the saved data looks at a bit level. Before getting back to saving to tape, like you saw in the intro, but with a bit more detail, I will spend a short time talking about the tape deck itself. But first, a little bit of history. Way back in the very first issue of Byte magazine in September of 1975, Don Lancaster, who'd already had a founding father type of influence on the home computer revolution by creating the TV typewriter in 1973, wrote an article simply called Serial Interface. In the middle of the 1970s, hard drives were reserved for the horrendously expensive minicomputer level and the monstrous mainframes still in use at the time, and only really expensive microcomputers had floppy disks. This had left the hobbyists with only two things to do when the power was turned off. Either writing all the code again, or paying up for floppies. With a good way to save data to inexpensive tape, there was suddenly a new mass storage media in town. Don's article, including nifty schematics, was enough to prompt 18 people to meet up on Friday, November 7th and the morning of the 8th of 1975 in Kansas City. Most notably, Bill Gates, still working at MITS at the time, was on the attendance list. Don's article had suggested using 16 cycles at 4800 Hz for a mark and 8 cycles at 2400 Hz for a space. But the consensus in Kansas City turned out to be in favor of using exactly half of those numbers, 8 cycles at 2400 Hz for a mark or a 1, 4 cycles at 1200 Hz for a space or a 0, still keeping the UART style start and stop bits and still enough to recover the clock frequency from tape. By the late winter of 1976, these efforts hit the press, and the March issue of Byte had a complete schematic for a tape interface in Don's article, Build the Bit Buffer. Even though the standard itself didn't succeed in making one universal tape format everyone could use, it certainly did make it clear that tape was a reliable and cheap mass storage medium, even if it was a bit slow. This is my simple universal modem design. You simply connect 4 jumper wires from your microcomputer, Arduino, and so on to the data in, data out, 5 volts and ground on the left side, and connect a 3.5mm mini jack cable on the right. The pin header jumpers here in the middle are for selecting which of the cable lines are for input, output, and ground. For my tape deck, I simply use a mini jack to RCA connector cable and use one channel for the output to aux and the other channel for input from line out. I've taken some liberties with the Kansas City standards with my actual software implementation. Excuses, I haven't had the time to write more than the basic routines to store and load data, and I've skipped the error correcting and start and stop bits completely for these demos. You can expect to see an update in my 6502 single board computer repo on GitHub soon to rectify that. Don's bit buffer is a bit too complicated for my taste because it assumes the input to be serial data along with a clock frequency reference of 64 times the baud rate and a serial clock of 16 times the baud rate. Instead of assuming everyone is going to use a 40-pin UART chip to interface with tape, I've gone with the assumption that everyone has some way of generating at least a square wave in software that'll be within a few percent of the two frequencies used. On the receiving side, I decided to leave out the clock recovery circuitry, and instead I'm assuming that you will use the modem with a computer, a microcontroller, and Arduino, something that can detect the intervals between the falling edges of a square wave. These are the two most important parts of the modem: the modulator at the top and the demodulator at the bottom. If you're being really pedantic, you might say that this isn't a modem at all because it doesn't do a complete job. The modulator only takes a square wave input from the data outline and smooths it into something resembling a sine wave with a bit of buffering. I would say that it barely qualifies because it does turn a digital signal into an analog one and thereby making data into audio, even though it does need the computer to do more of the lifting than just provide zeros and ones. The demodulator takes the audio input from the mod inline and passes it through a comparator that turns the audio tone into a rather clean square wave. You might notice I didn't add any extra filtering on the demodulator input. The first reason is that I didn't need it to get clean data through, and the second reason is that the modem will be more universal if you don't have to change filter values on both input and output. Of course, the modem wouldn't be very universal if you could only use it with old tape decks, so let me show how it looks when it's hooked up to a modern PC. Actually, you can use it with pretty much anything that'll record and play back audio. Here I start by writing some text, pressing print screen on the keyboard to save it to RAM, and then clearing the screen by pressing escape. I've set up my system so the F2 key starts the save routine and F3 starts the load routine. I'm using 1200 baud Kansas City standard here, which is actually a bit misleading as the highest speed mentioned by Lancaster in the articles mentioned earlier was 600 baud by doubling the frequencies. Instead, I keep the frequencies the same and instead use 2 cycles of 2400 Hz for a 1 and 1 cycle of 1200 Hz for a 0. This is more like the BBC Micro, except I haven't implemented the error correction for that interface either. The computer is just connected to the modem with an iPhone mini jack splitter cable and a cable to the mic input and earphone out of the USB sound card. I couldn't get my MacBook to register the modem as a microphone, so that's why I used the external sound card. Sadly, I had some issues with extra noise while recording this, so I didn't really get the same results as when I did the first tests on my workbench, but I guess it all adds to the experience. But either way, at least the text I saved was recovered correctly. I have a feeling it's either a bad ground connection or USB noise from my USB-C hub. You can certainly hear the scratchy sounds in the audio. I don't seem to have the same problem with the tape deck, but I don't think I'll get away with not implementing the housekeeping bits at all, even though this is technically faster. Besides hearing the peaks as a stutter in the audio, you can also see the noises way outside the envelope here. But let's have a look at the beginning of the data. First, it needs 1 or 2 cycles to stabilize in the beginning, and then it just keeps outputting leader marks or 1s until it reaches the first 0. Technically, the waveform is inverted here, as this is a cosine wave instead of a sine, but it doesn't really matter because all we care about is the distance between zero crossings. The transition you see here is 2 2400 Hz waves that together make a 1 bit, followed by a single 1200 Hz wave that makes a 0 bit. Even though I haven't implemented start and stop bits for every byte, I did need a way to synchronize the start of the recording, so I have 1 start bit for every recording. Since the receiving software in its most basic form is just a shift register that shifts in new valid bits under a certain period threshold, data isn't accepted until a leader byte of 7F hexadecimal is seen after a minimum amount of ones before. The Kansas City standard specifies a minimum of 5 seconds of ones, but I've relaxed that a lot in my software for now. Since the saved data from the screen starts out with a lot of zeros, that's what we see for the first long part of the recording. When the text on the screen starts, we see the uniform envelope turn into something a bit more substantial. If we want, we can even start decoding the bits by hand. If we zoom in a bit, we can start manually doing the same thing the receiving computer is doing. Of course, it's easy for us to see that first we have 2 short waves, followed by a long wave, but the computer can only detect the falling edges and the zero crossing, and then use that to determine if the period was above or below a number that represents the middle frequency of 1800 Hz. 2 pulses above 1800 Hz count as a 1-bit, and 1 pulse below 1800 Hz counts as a 0-bit. Since we don't need to recover the clock like Lancaster's bit buffer, or with a PLL or something like that, this works just fine on my 6502, and the BBC Micro for that matter. You might have noticed the amplitude difference between the 2 frequencies due to the fact that the RC filter used is a low-pass filter. I could probably make that a bit more even without changing the board layout by swapping out a few capacitors and resistors. To speed things up even further, you can skip the second 2400 Hz pulse, making the data a bit more uneven by making ones take up half as much tape as zeros. If 50% of the bits are ones, this will increase the speed and capacity by 25%. Another way would be to use only the half waves, changing the frequency at every zero crossing instead of just once per wave. For the 6502, this is certainly possible to keep up with by simply changing the active CA1 edge while receiving the data. A third way would be Lancaster's suggestion of simply doubling the audio frequency. Depending on how many of these tricks you put together, you risk sacrificing reliability for speed and storage capacity, and as many people remember, the result was often the worst of both worlds. For instance, the Commodore 64 dataset forever stuck at 300 baud without being particularly more reliable than the BBC Micro. I'm honestly not completely sure what came first, if I wanted to save data to tape and that made me fix up the tape deck, or that I needed a good enough reason to fix it and saving data was just my excuse. Either way, it was a lot of frustration, but also a lot of fun, and at least now it's saved from going into the trash. After 50 years, it was completely gunked up, and most of the moving parts were completely stuck and couldn't even be forced into position. After cleaning out and relubricating the whole thing, it still didn't play right, but at least it played a little bit, kind of, for a while. But then it didn't. I knew the motor was fine, but changing the motor run capacitor made it spin like new again. I have that story in more detail on the Hackaday.io project log for the Simple Universal Modem linked in the description. So, did it work the first time? Actually, I was surprised how well it worked with my minimal effort on software, but of course I still have to make it software compatible with some of the tape formats out there. The problem with the way it is now is that the leader byte might be misdetected, causing a bad start, making the whole thing garbage, or, as you'll see soon, offsetting the data enough to ruin it. Most of that would be solved by simply implementing start and stop bits in software, maybe even the block scheme of the BBC Micro. I'm sure there are a bunch of people out there that would like an easy way to recover data from their old tapes for the Beeb or the Commodore 64. Of course, if I'm being honest with myself, I know the easy way is just to load the tapes onto a PC and software decode them, but sometimes it's good to have alternatives. I haven't tried yet, but I can imagine the Simple Universal Modem would work fine with the Raspberry Pi's GPIO pins, even though they are 3-volt pins. What you see here is the full-speed version of the recording and playback I used for the intro, including all the failures. That'll give you a feel for exactly how slow 300 baud actually is. I'm pretty sure the first playback failure is actually just me pressing 2 for 1200 baud, messing up the whole thing. The second time I don't rewind the tape far enough, but still manage to get readable text. And the third successful time, my impatience just makes me stop loading a bit after the text. If you want a simple and cheap way of saving data to and from a computer from the 70s or 80s, I suggest you use a modern SD card. But if you really want to feel what using a 50-year-old computer really felt like back then this is a great way to try it. Even though I only recorded at 300 baud bitrate here, I actually had no problems recording at 1200 baud when I was testing. Maybe it wouldn't be this easy if I was using cassette tape instead of a quarter-inch tape, which probably gives me a bit better bandwidth, but either way, I'm super happy with the quality I get out of the used tape I have, which is actually from the 60s and 70s. I haven't even experienced a dropout yet. If you'd like to make your own simple universal modem, or clone my 6502 single-board computer for that matter, you'll find links in the description for both projects on hackaday.io, including build instructions, and the complete source code for both hardware and software you'll find on GitHub. I'm really happy every time I see someone is interested enough to make it this far into one of these videos that don't really have the broadest appeal. So let me take this opportunity to say thank you very much for watching this far. If you're still around, I'm sure you know what to do if you want to see more of this stuff. In the future, you can expect videos about hardware and software for retro computers and obscure old ICs in general. More specifically, I plan on getting MS Basic running on my 6502 computer and interfacing it to some older sound ICs and other obscure dip chips from the 70s and 80s. Who knows, I might even try my luck with an 8-inch floppy drive, even though those take some more effort than tape and I haven't been able to find one I like yet. I also have some 8051 microcontrollers lying around, so of course I have to make a single board computer out of those eventually. If there's anything you'd like me to clarify, have questions in general, or have any kind of comment, then please leave it below. I really appreciate all the feedback I can get. While we wait for this last demo to move along at 300 baud, I have a little bonus info to give an idea of how much data can reliably be stored this way. I can tell you that the reels I use here are 800 feet long, which is 21,600 inches. Since I run the tape at 3¾ inches per second, that will give us 5,760 seconds of runtime per side. 11,520 seconds at 1200 baud instead of 300 baud will give us just around 1¼ megabyte per tape reel, if we assume we have to use 11 bits per byte. If instead we run the tape slower at 1 7/8 inches per second, that will give us a whopping 2½ megabytes of storage per reel. Not bad for a storage medium from 1972. Thank you so much for watching.